So now, before we start with our simulation, we need to create a mesh. And you may ask why we need a mesh. Why do we use a mesh? So it's really hard to calculate for the software the stresses and strain for this model. So that's why we need to divide this a big problem into small problems in small elements and nodes to calculate stresses and strain and displacement for those small elements. So basically, in finite element analysis, discretization is a critical process in which continuous CAD geometry is divided into smaller elements, but the shape of the elements decide what kind of mesh do we create. So basically, we need to create a proper mesh to get proper results. We also have to be careful what kind of mesh do we create, because the shape of the element affect the final result, stresses, displacement and strain. And if we have a distorted element, then our result will be inaccurate as well. The number of element plays a critical role, so we have a lot of elements that takes a lot of time and a lot of computational memory. So we have to balance the number of elements and with the shape of the elements. So we want to create smaller elements in the area where we predict the higher stresses. For example, in our case, this part will bend and the highest stresses will be here and here and in this region and in this region. So SolidWorks for solid bodies uses tetrahedral elements with the ideal shape of 60 degrees and of equal length edges, which are have to be 4 nodes per element. So we want to maintain this shape as well. If you have a model and on the model you have a lot of fillets, chamfers, holes, engraved text, you may want to get rid of that because those features don't affect on the strength of the model. So due to this, the mesh on those features will be distorted and then you're going to get bad results. So how can we improve those features? For example, in our case, we have this flat and for the meshing, we don't need this flat because this fillet will only make trouble for our mesh. So when you have a big model and you have a lot of fillets, chamfers, and you don't know which fillets and chamfers will be good to suppress, you can go to mesh and right click and simplify model for meshing. So let's click here. So here on the right side we have features and we can choose what we want to simplify. We can click here and we can choose here fillets, chamfers, hole, extrudes, or we can go with all. So let's go with all. So here we have a simplification factor. Let's have this factor as 0.1, and here we can have a feature parameter. And now let's click on find out, and the software found out that we should maybe suppress uh, this at once. Let's click on the fillet. Now we see that this fillet, and here we can click suppress. So let's click suppress, and now our fillet is gone. Let's exit. So now you are going to see the other way. So you can use the simplification method here and you can suppress, or you can use fillets chamfer before you start your study analysis. So let's go to the mesh and let's active SolidWorks configuration. I'll choose no fillets is back. Let's go to model and let's find this fillet. Let's click here. So this is the fillet one. Right click here and suppress it. So this is also the option, but now we have a problem here. As you can see, we also suppress automatically split line for here. And now if we go to our solid body, we can see that we have an error here with pressure, because now it's not defined the surface of the pressure. So we have to go to model again, and we will have to recreate the split line, because when we were creating the split line, the sketch had a relation with fillet, and now the fillet is gone. So now let's go to fillet and let's unsuppress like this, and let's unsuppress the split line. Let's open split line 4 and let's go to edit sketch like this. And now as you see, we have a coincident relation here, and this is the relation between this line and fillet. We want to delete this, so right click and delete it. Let's insert a center line, and here like this vertical center line, let's go to smart dimension. Let's define an angle here like this and click OK. So let's click OK and let's delete this coincident as well, and let's define an angle here like this and OK. And now our sketch is not connected to this fillet. Let's exit sketch like this, and now we can go to fillet. We can right click suppress, and our split line is here and we don't have any error here. So if you look at this, you can see that this warning here, and you don't have this warning because I have previously created a mesh, and now this warning is here because of the mesh. And now we are ready to create a mesh. So now we are ready to create a mesh. So let's right click on the mesh and let's go with the create mesh. So here we have mesh density, and we can move this to the right and to the left. So if we move this to the right, then we are going to have a finer mesh and we are going to have more elements. and that's going to increase the time of the simulation, and that's going to increase the memory as well. And now here we can go with the bigger elements. So that's going to increase the time and simulation as we discussed. So this is really up to you on how you're going to set this. You can go with the default by clicking here reset. If you open this mesh parameter here, you have some parameters. So let's go with the standard mesh here. So make sure this is checked, and here we have global size of the element. So this is 4.9 millimeters, and here we have tolerance. The tolerance is 5% of the global size of the element, and if the distance between two neighbor nodes is smaller than that, the nodes are then merged. The upper limit of the tolerance is 30%. So when you want to create a mesh, always go with the default first. So let's leave everything as it is, and let's go to the reset, and let's click OK. Now we have created a mesh. So if we go closer, we see that we have elements, and the perfectly shaped elements will be like this. We have 60 degrees here, here, and here, or all three lines are equal. Here, for example, we don't have perfectly shaped elements. We are never going to have perfectly shaped elements, but we want to have a good shape of the area where we predict higher stresses, since this is going to be bended, and this is going to bend. So we predict that we are going to have higher stresses here and here. So in this region and in this region, we want a well-shaped element, because then our result stresses, strain, displacement will be more accurate. Now let's go to the mesh. Let's click here on the mesh, and let's go create mesh plot. And here we have some options. We have an aspect ratio and Jacobian. So aspect ratio in Jacobian measure the element quality. So the aspect ratio is the ratio of the longest normal to the shortest normal of the element, and the normal is dropped from the vertex node to the opposite face of the element. So the aspect ratio measures how stretched out the element is, how distorted the element is. So if we have a big aspect ratio, that means that this element is more distorted. So our goal is to have the smallest aspect ratio as possible of each element. Ideally, it would be that aspect ratio would be below 5, but everything below 10 for us will be acceptable. Uh, Here we have a Jacobian, but Jacobian is not the graphical representation of the element. Quality is numerical representation, and Jacobian can give good results after the simulation. And here only Jacobian predicts the quality of the element. So first let's go with the aspect ratio, and let's click OK. And now if we look here on the left side, we have a new folder, mesh quality, and we have mesh quality 1 aspect ratio. So here we have a legend. So our aspect ratio is from 1.35 to 9.5. So the biggest aspect ratio is 9.5. And if we look closer, we see that here we have the biggest aspect ratio on this edge, because here we have some flattened. We can see how flattened this element is. If you look down here, here we have a good shaped elements, and if we look at this back here, and also pretty much good. So here on the other side as well, we have distorted elements. So let's go to mesh quality, right click, chart option, and let's click here, show maximum annotation. And now we can see where is the maximum aspect ratio. Let's click. So let's go here. And now we see that the maximum aspect ratio is here and here. The stress result won't be so much accurate, but here are not our biggest stresses, and biggest stresses will be here and here. So generally this would be acceptable. Now let's go to mesh. Let's right click, and let's go to detail, and here we have some information about our mesh. So we have a mesh type, we have element size, mesh quality, we have a total number of 12,000 nodes. So we have over 12,000 nodes, and here we have maximum aspect ratio of 9.5, and here we have a percentage of element with aspect ratio below 3, and we have 99.7, and this is the time to complete mesh, which is 4 seconds here. So the number of nodes affect on the time to complete the mesh. So we don't want to have a lot of nodes, and we want to have lowest as possible maximum aspect ratio. So let's exit, let's go to our mesh again, right click and create mesh. So now we have a global size element which is 4.9. Let's go with 2.4 like this, and let's okay. Now as you see, we have a finer mesh, our elements are smaller. Now if we go to our mesh and right click in detail, now we can see that we have 86,000 nodes, and before we have 13,000 nodes. So we have much more nodes, and the maximum aspect ratio is now 6.5, but the number of total nodes, it's not really acceptable for us. So let's exit, let's go to mesh, let's open here mesh quality, and let's double click on the mesh quality aspect ratio here, and now we see that we have the maximum aspect ratio here on this edge, not here. Here they are pretty much good. Now we have a problem here, but this is acceptable. Now let's go to mesh again, right click on create mesh. Let's go with the reset to default values. Now if you notice, if you change the density, then the size of the element changes. But let's go to the default reset and let's turn on automatic transition, and let's see what kind of results we get. So what is automatic transition? When automatic transition is checked, the program automatically applies match control to all fine details of the model. So the generated mesh is finer at the areas with small features. So everywhere where we have small features, the mesh will be denser. Let's click OK, and let's go to mesh details. And now we see that we have 15,000 nodes and 9.5 aspect ratio maximum in 3 seconds. So this is more than the first case. Then we have 13,000 and aspect ratio about 9 something, and this is how you create a standard mesh. In this first case, we have used our default parameters. We created a mesh that was acceptable for us, but now we are going to try to get better mesh. So that was all for this video, but we will be continuing after mesh topic in our upcoming video, in which we will cover curvature based mesh and other aspect of mesh details. So stay tuned.
Do subscribe our channel and hit the bell.